Welcome friends in the fourth lecture of the fluid mechanics. In this lecture we will see the next property. So our next property is viscosity. And it's presented by mu. This is also termed as dynamic viscosity. You can also add here dynamic viscosity. No. So what is dynamic viscosity? So let's consider this one. So here we are considering a solid surface and on this solid surface some fluid is flowing. These are the fluid layers. Right now that one layer is also in this solid surface. So if we want to analyze this fluid flow, so I'm considering a cross section over here. We are considering this cross section. So Newton investigate this type of fluid flow and he provide that first that if we are saying this is the solid surface and the fluid layer exactly stick to this solid surface has zero velocity, as we discussed in our first lecture. That is, the condition is no slip condition. No slip condition means the velocity of this layer is zero. And at the topmost layer, as there is a flow here, so this topmost layer is flowing with some velocity v. So over this cross section, when we are analyzing this cross section, so this layer has zero velocity and this layer has v velocity. So during the experiment it is found that for the particular fluids that are defined as Newtonian fluids like water, this is the profile that is set here. What is this profile? So we are saying that here is the velocity is zero. For this layer there is some velocity, because between this layer and the solid surface the forces are the cohesive forces that are so strong that this layer can't slip over this one, no slip. But between this layer and this bottommost layer there are adhesive forces. In between these two layers the forces are cohesive forces that are less strong. That's why this layer will slip little bit. That's why there is some velocity of this layer, this much. Now again there is cohesive forces and this layer will move more faster than the lower layer. It has more velocity. Similarly, as we are going upside, so the velocity keeps increasing. Velocity will keeps increasing. This is experimental evidence. So the topmost layer velocity is v, bottommost layer velocity is 0. So if I am considering these two layers which are at a distance dy apart, so I am drawing this much here. So one layer had some velocity, another layer is this much of velocity. The distance between two is dy, and this is our y coordinate, and in the flow direction has x coordinate. So now that I'm saying this lower layer velocity is u and this layer velocity is u plus du, that is more than the lower velocity. So we can say that the difference in velocity between these two layers is this much. So this is u. So this part of this velocity, this part is also u. So the remaining part is actually du. Alright, so the remaining difference in these two velocities is du. So we are defining here is a term that is termed as velocity gradient, that is defined as change in velocity with respect to the y, that is change in velocity normal to the flow direction. X is the flow direction and we are going to see the change in the normal direction of the flow. So this term, that is du upon di, we are defining velocity gradient. Velocity gradient. Velocity gradient here. Right. So now for particular types of fluid, like for the water, the velocity gradient is maximum between these two adjacent velocity layers, these two layers, because here the velocity is 0 and there is a sudden change in the velocity. So we can see here this whole velocity, the difference is equal to this one, because here the velocity is 0, here there is some velocity. Now again for these two layers the difference is this much, for this one difference is this much, for this one difference is this much, and when we are going upside the difference is going to decrease between two layers. This is the experimental evidence. So we can say that is as we are moving from bottom to top layer, the du is going to decrease, because you can see here in between these two layers difference is too much, maximum, then difference is less, then less, then less, then less, and up to this point it is almost approximately 0 here. So as we are moving from the bottom to top layer, the du is going to decrease. That's why the velocity gradient du upon dy is also going to decrease. Right, the velocity gradient is also going to decrease. Now, so as we know, the flow is happening due to the shear forces. We are applying some shear force like that over this layer. That's why there is a flow here. So when we apply the shear force, then the shear stress will induces in between two layers. What is shear stress? Shear stress, if that I am saying Fs is the shear force, then tau s, that is the shear stress, will be equals to shear force by area, that is area between these two layers, surface area. So this is our shear stress. So shear stress will induces. So if we are talking about the bottommost layer, the shear stress is maximum here, because shear stress is the resisting force, that is induced force. That's why when this is maximum, this layer is not moving, that is maximum value, because the shear stress, the resistance is maximum here. But as there is a movement here, so the value of stress is less. That's why this layer and this layer has some relative velocity. Now again, as the difference between two layers is velocity, the velocity of two layers is going to decrease, means the shear stress is also going to decrease, because when we are moving from bottom to top side, the layers are moving faster and faster, means the resistance is going to reduce from bottom to top. This is 0, this is here the stress is maximum, and as we are moving from bottom to top layer, the stress is going to reduce here. So we can also conclude that is as we are moving from bottom to top, we are saying bottom to top, the shear stress is also going to decrease. Right, as we are moving from bottom to top, the shear stress is also going to decrease, and here the velocity gradient is also going to decrease. So means from these experimental conclusion or data, we can conclude that is shear stresses are proportional to velocity gradient. Right, why? Because as we are moving from bottom to top, this velocity gradient is decreasing, and as we are going from bottom to top, this shear stress is also going to decrease. So we can say that there is shear stress is proportional to velocity gradient. Means as the velocity gradient is going to decrease, the stress is going to decrease. So as the velocity gradient is maximum at the bottom, the shear stress is also maximum at the bottom. As the velocity gradient is approximately 0 at the topmost layer, between the topmost layers, the shear stress is also approximately negligible between the topmost layer. So this is the case here. Now here, so in this case, we are providing this definition. I am introducing a proportionality constant here. That is like that. So tau is equals to mu du by dy. So here mu is the proportionality constant, and this is defined as dynamic viscosity. This is defined as dynamic viscosity. So actually the viscosity is nothing, it's a internal resistance between the layers, and it will try to resist the layer moment. So it is the frictional resistance between the layers. So what is the sense? What is the sense of physical resistance? So we can understand, if let we are saying we have two fluids, one is water and one is honey. So we can easily see that is the resistance between the layers of water is less, that's why the flow is easy, but the resistance between the honey layers is more, that's why the flow is typical, or the resistance is more, that's why the flow is harder. Means the flow between the water layer is smooth than compared to the honey layers. So from here we can say that is the honey is more viscous compared to the water. Honey is more viscous compared to the water because the viscosity or internal resistance between the honey layer is more, and the viscosity and internal resistance between the water layer is less. Alright, so means we can say that is mu or viscosity is internal frictional resisting force between the fluid layers. Alright, so viscosity is internal frictional resisting force between the fluid layer. Now so I can rewrite this one like that, that is mu is equals to tau upon du by dy. So when we are defining mu is equals to tau du upon dy, so for units we know the units of the stress is Newton per meter square, and unit of velocity is meter per second, and unit of length is meter. So let here the meter will out, the second will be upside, so this will be Newton per meter square into second, and we know there is Newton per meter square is also defined as Pascal, so we can also termed as Pascal second. Alright, now in other form of units we can also define, that is, let if I am defined like that in CGS technique. So I can write that is 1 Newton per meter square second is equals to, so 1 Newton is equals to 10 to power 5 dyne. Second is second, sorry, this is not like that. 1 Newton is equals to 10 to power 5 dyne into second, and CGS meter will be centimeter, so this is 10 to power 4 centimeter square. So from these two, this will out, this is only power 1, so this is 10 dyne second per centimeter square. Alright, this is, so 1 Newton per meter square second, that is Pascal second, is equals to 10 dyne second per centimeter square. This term is defined as poise. Alright, so we can say that 1 Pascal second is equals to 10 poise. Similarly, we can say that 1 poise is equals to 1 by 10 Pascal second, that is also equals to 0.1 Pascal second. 1 poise equals to 0.1 Pascal second. Now let little bit more. As 1 meter has 100 centimeter, similarly 1 poise is equals to 100 centipoise. One poise is equals to 100 centipoise. Alright, so this is the unit conversion for this case. Now let's see a little bit more. Look at this one. Mu equals to tau du upon dy. So I'm drawing a graph. And I'm saying I'm taking tau at y-axis and du upon dy at x-axis. So from the slope equation we know that is slope is equals to dy by dx. So let's consider this is dy and the whole term is dx. So we can define mu is a slope actually. So if we are defining like that, so this one, so this is dx, this is dy. So actually this is slope here. So we can say that mu is presenting a slope when we are plotting a graph between du upon dy, that is velocity gradient, and shear stress. And this slope is constant because when we draw the graph between this one, from this equation, we know the slope will be remain constant. So this line is presenting mu. So means as slope is constant, so if you are moving from this point to this point, if I am moving from this point to this point, so you can see here at this point the du upon dy is 0. So du upon dy is 0 at between top layers, and at this point that I am saying this point, the du upon dy is maximum, some finite value, and we know du upon dy and tau is maximum at the bottommost layers. So when we are moving from this point, let I'm saying point A to B, so actually this is point A to B, so actually I'm moving from the top layer where tau and du upon dy is 0, this is B point, sorry, this is A point, to the point B where du upon dy and tau is maximum. So this is our B point, this is our B point. So when we are moving from A to B point, the slope remains constant. Means when we are moving from A to B point, the slope remains constant. Slope means viscosity. Viscosity remains constant when we are moving from the point A to B. Alright, now let I'm saying this is particular slope and I am presenting by mu A. Now that if I'm saying this is another line for some another fluid, let I'm presenting this is mu B. So the slope of this line, that is for mu B, is less than the slope of this line, that is mu A. Means for this particular types of fluid, the viscosity is less compared to this particular type of fluid because the slope is less. So I can say that is mu B is less than mu A, but throughout the slope remains constant. But for two fluid comparison, we can say that there is mu B for the fluid B, the viscosity is less compared to the fluid A here. Right, so this is happening. This particular formula is termed as Newton's law of viscosity. That is, tau is equals to mu du by dy is termed as Newton's law of viscosity. Alright, this is termed as Newton's law of viscosity. Alright, so now let's consider more things. Let I'm saying for this case, it will look like this one. Some another fluid. But I'm drawing again. So this is the line for some another fluid, and this fluid is not behaving like these fluids because here the slope of this curve is variable, and in this curve the slope is constant. So if we are viewing this one, in this case we can see here the slope, let I'm taking the tangent at this particular point, so tangent is look like this one here, and at this point the tangent is around this one, at this point the tangent look like this one, for this one the tangent look like this one. So means as the tangent is, you can see here the slope is going to decrease when you are moving from this point to this point. So means the slope is not constant, slope is variable here. So means this is not following this particular type of law, that is Newton's law of viscosity. So when the fluids are behaving like that, the fluids are termed as non-Newtonian fluids. So means if we are defining this type of fluid, these are termed as non-Newtonian Newtonian fluid. Newtonian fluid. And these fluids, this one and this one, are termed as Newtonian fluid. Newtonian fluids, like water, oil, these fluids. Most of the engineering fluids are forming in the category of Newtonian fluids. Some hydraulic fluids, water, and all this. And there is very particular different brands for these types of fluid. Like if I am saying milk, sewage sludge, chocolates, so these types of fluid are not behaving according to this law. They have different nature. The slope is variable. These are termed as non-Newtonian fluid. Alright, now let few more things. Consider this line. Sorry. Considering this line, that is x-axis. I think the line is not going to straight. No problem. So for this line, for the x-axis, the slope of this line is 0 actually, because we know as we are moving from this point to this line, from this line to this line, the slope increasing. For this line, the slope increasing, and for this line the slope is maximum. So we can see here at this, for this line the slope is 0. So if the slope is 0, we can say that there is mu is 0 for this case. Means the viscosity is 0. So what will happen when the viscosity is 0? So when the viscosity is 0 means the internal resistance between the layer is also 0. Means the layers are not offering any resistance to each other. So if there is no resistance, in that case the fluid is very much difficult to handle. Little bit disturbance, the fluid will slosh out. Means if there is no resistance, almost zero force required to the flow, and you can't resist the fluid from sloshing. So this type of fluid, when the viscosity is 0, when the mu is 0, is termed as ideal fluid. When the viscosity is 0, is termed as ideal fluid. Alright, now let's consider this one, y-axis. So here we can say that there is here the mu is infinity. No, we will consider like that. Here mu is not infinity actually. Here on this line the du upon dy is 0. For this line the du upon dy is 0. Means there is no velocity gradient. Means if there is no velocity gradient, so means we can say that these types of substance are termed as ideal solid. Ideal solid means when you are on this line, you are keeps applying the force continuously, but there is no movement between the layers. So these are the ideal solids. But in our universal system, there is no ideal solid. That's why the real solids are little bit, not little bit actually, real solids are different from these ideal solids. So means if I want to draw the line for real solids, I will draw like that. Sorry, line is not going to straight. So for this case, I'm drawing line like that, almost like that. It's okay. So means there is a deviation between the ideal solid and the real solids. This type is defined as real solid. These are the real solids, because when you are applying the force, there is little bit velocity gradient occurring in this one. So actually not velocity gradient, there is a movement between the layers. Definitely for every material there is a limit of the force after which the solid will start to deform, but that deformation for solid is not termed as flow. Why? Let's see here. Again, let me consider this diagram, and I am considering this particular section. Alright, and I am saying there is a fluid element in between these layers. So I am drawing here. So I am saying this is A, this is B, this is C, this is D. Alright, so let here at AD is this part. AD, the velocity is U. BC, the velocity is U plus du. And the distance is dy. So let I'm saying, due to some force, that is here force, this point will move here around in the time interval dt. That I'm saying this is B dash, and this point C will move here. This is C dash. So B point will move to B dash and C point will move C dash in time dt. Alright, so let I want to calculate what is BB dash. So BB dash is the distance traveled in the time dt due to the relative velocity between these two layers. So the relative velocity between this layer and this layer is du. So as we know, that is speed is equals to distance upon time. So distance will be equals to speed into time. So I can write BB dash, that is distance travel in the time interval dt due to the relative velocity du. So BB dash is du into dt. Alright. Similarly, if I am saying due to this force, the deformation is at d theta. Deformation between this one, shape change is d theta. So we can assume this is an arc. BB dash is an arc. So for the arc definition, we can say that there is BB dash is equals to, so there is arc is equals to radius, that is dy, into angle, that is d theta. So this is dy d theta. This is also BB dash. So these two terms are both are equals to BB dash. So by comparing them, I am comparing them, du dt is equals to dy d theta. So rearranging the term, I can write that is du upon dy is equals to d theta upon dt. Alright, now as we know Newton's law of viscosity, tau is equals to mu du upon dy. So I can replace this term du upon dy by the term d theta upon dt. So I can write tau is equals to mu du upon dy is also equals to mu d theta upon dt. And yes, when we provide the definition of fluids in our first lecture, said that shear stress tau is proportional to rate of strain. Shear stress is proportional to rate of strain for fluids, and for solids tau is proportional to strain. So solids are suffer strain due to shear stress, due to shear force, and liquids or fluids are suffer rate of strain due to shear force. Alright, that's why the fluids are differ from solids. Alright.